All right, so let's go ahead and get started. So last week we started talking about magnetic fields, magnetic forces, and the Lorentz force law. So to remind you what the Lorentz force law said, this told you what the force was on some charged particle due to both an electric field and magnetic field, such that the force that a particle experiences is going to be equal to Q, the charge of the particle, times the electric field. So this was a portion that we had seen quite a while ago. This was on the PHYS test. And then the second piece was the force that the particle feels due to the magnetic field, and that's going to be equal to the charge times the velocity crossed with the magnetic field. Okay? And we went through a whole host of problems that guided us through how cross products work. And so we'll remember that if I had two vectors, some vector A crossed with some vector B, where we could say, for instance, the vector A points this way, the vector B points that way, and there's some angle between these two vectors, that the cross product A cross B can be written as the magnitude of A times the magnitude of B times the sine of the angle between these two vectors times the unit normal vector. And this is what we were determining last week using the right-hand rule. So this is determined by the right-hand rule. Okay. Now, we also began talking about the way that magnetic fields behave, or the way that they look from different arrangements of current. And so we saw, for instance, that if we had some current-carrying wire going to the right like this, that this would have some magnetic field that goes around this. And again, this was another form of the right-hand rule that we used to determine what the direction of the magnetic field is here. So this is what in the video I had called right-hand rule 1, right-hand rule HR1 corresponded to this right-hand rule. So take my right hand, take the fingers of my right hand, point them in the direction of the first vector, curl them in the direction of the second vector, thumb points in the direction of the normal vector. But there was this other variant of the right-hand rule, and we'll be getting more into this one today. And this one tells us what the direction of a magnetic field is when I know the direction of some current. And so what right-hand rule number 2 says, so this is RHR2, is take your thumb and point it in the direction that the current is going, and then my fingers are going to curl in the direction the magnetic field goes. And so when I do that, what I see is here, the magnetic field is going to go around like this, so that the magnetic field is going to be pointing out of the page above, and it's going to be pointing into the page below. Okay? So any questions about what I just laid out here? Yeah?
So just to reiterate, is pointing in the direction of current?
Thumb in the direction of current. So thumb in the direction of current. Yeah, it's almost a little easier like that because you can kind of visualize your thumb going the way the current goes, and then your fingers are just wrapping around the direction of the magnetic field. Yeah. Yeah. Other questions? Okay, so let's get back into some of the questions that we left off with last time, and this is going to lead us back through some of these questions where we had some charged particle that's moving in the presence of a magnetic field, find the direction of the force, or if we know the direction of the force and the velocity, what's the direction of the magnetic field? So this one says an electron is in a magnetic field that points into the page. Is my polling just broken on all of these? Okay, so we don't have polling on. Why is? Okay, well, this clearly makes sense. Okay, well, we'll do this question, then we'll talk about it. But this one says an electron is in a magnetic field that points into the page and experiences a magnetic force to the right. Which of the following is a possible direction of the velocity of the electron that would cause that force? So go ahead and talk about this one. I'll see if I can fix the polling so that it works. Okay, so let's talk about this one. It sounds like a lot of you guys remember these from last week. And so we'll just go through this one kind of quickly. So this one says that we have some magnetic field that's going to be pointing into the page. We have some force that's going to be pointing to the right. And so We also know that this is an electron, so our thumb is constrained to be pointing to the right, so that's going to be pointing this way. Our fingers are going to have to curl in, and so my thumb's fixed to point to my left, your right, and my fingers have to curl going in like this. And so that means that when I let my fingers go down, they're going to be pointing down, but because this is an electron, this is going to be flipped. It's going to go the other way, so it should be up. Okay? Let's move on to the next one. Okay, so this one's working. So this one says a long straight wire is aligned with the y direction carrying an upward current. The wire is in a region of magnetic field that points into the page. What is the direction of the force that this wire feels? Now, this was something I neglected to add here, but it carries through pretty naturally from the way that we talk about the force on a charged particle. So if you think about a wire, it really is just a tube that charges can flow through, and so what we would say is we have some positive charge that's in this wire, and what's constituting the current is the fact that these charges are going to be moving. And so what this allows us to do is it allows us to take this equation, F is equal to Q V cross B, and kind of rearrange it. So if we look dimensionally at what the product of the charge and the velocity is, this is going to be QV. If we want to look at the units of this has units of coulombs times meters per second. But we can kind of rearrange this and write it in a slightly different way. And that's to say that I could write this as a current times a length, right? Because if I look at a current times a length, this has units of coulombs per second times meters. So dimensionally, these two things are going to be the same. And so what that tells me is I could think about the force on a current carrying wire in a very analogous way to the way that I find the force on a charged particle if I write this equation instead as F is going to be equal to IL cross B, okay? Where L, vector, is denoting the direction that the current is going. So, and for us, that can be lazy with my notation. It's actually better for us if we say that this is Li vector cross B. But there are various reasons why you really don't want to define the current vector. But this just says the direction of the current crossed with the magnetic field. Okay. So look at this question now. And so this one says that we have some current that's going to, or some wire that's aligned with the y direction carrying an upward current, and the wire is in the region of magnetic field that points into the page. We want to find what the direction of the force is acting on this wire. And so follow kind of the same process that we went through, and only now, instead of thinking about your fingers as the direction of the velocity of the charge, now we're going to say it's the direction of the current. Okay, so go ahead and talk about this one. All right, so let's talk about this one. So this one says we have some current that's going to be pointing up. So conveniently, I have this drawn here already. So we have this current that's going to be pointing up, and there's some magnetic field that's going to be pointing in, and we want to find what the direction of the force is acting on this wire. Okay, so in order to do this, apply the right-hand rule, same way we have been before. So we take our fingers, point them in the direction of the current, curl them in the direction of the magnetic field, and our thumb points in the direction of the force, which in this case is pointing to the left. Okay, let's look at another one. Okay, this one says a long straight wire is aligned with the x direction in a region of magnetic field that points upwards. As a result, there's a magnetic force in the wire that points into the page. What is the direction of the current flowing in the wire? Okay, so go ahead and think about this one. Okay, so let's talk about this one. So we have our mystery wire here. So we have this horizontal wire that has some current flowing through it, but we don't know what the direction of the current is. But we do know that it has some force acting on it that's going to be pointing in, and it's in the presence of a magnetic field that points up. So we have to kind of decide, does the current flow to the left, does it flow to the right, or there's not enough information to figure this out. turns out that we do have the right amount of information, but we just need to apply the right-hand rule to see why it's going to be pointing in the direction that it does. And so what we can do is we can first start by taking our thumb and point it in the direction of the force. So force is going to be pointing in, and whatever direction we end up pointing our fingers, it needs to be such that when we curl our fingers, it's going to be pointing, the curling of our fingers is going to be pointing up. And so that says thumb is going to be pointing in. My hand needs to be pointing to the left in order to curl my fingers up. And so when I uncurl my fingers, that's the direction of the current. And this says that the current is going to be pointing to the left. Okay? Any questions about that one? Okay. Moving on. Okay, this one says the long wire is in the region, Jesus, it's Monday morning, I can't read. The long wire below is in a region in which the magnetic field points out of the page. The force on the wire is upwards. What's the direction of the current in the wire? Same kind of question, just a little bit different orientation of the magnetic field and the force. So go ahead and talk about this one. Okay, so let's go ahead and talk about this one. So, very similar situation to the one we had last time, only the direction of the force and the direction of the magnetic field are a little bit different. And so, the direction of the force here is going to be pointing straight up, the direction of the magnetic field is going to be pointing out. And so, what we want is for our thumb to be pointing in the direction of the force. Our fingers have to curl in the direction of the magnetic field, and then when we uncurl our fingers, that's going to be the direction of the current. And so that tells us that I is going to be going this way. Okay? So let's go ahead and move on to the next one. Okay, this one says the long wire below is in a region in which the magnetic field points upwards. The force on the wire points upwards. What is the direction of the current in the wire? Go ahead and talk about this one. Okay, so let's talk about this one. This one's a little bit funny because this one, we have some force and some magnetic field that are in the same direction. And we want to determine what direction of the current, what direction could the current be so that this is the situation. And it turns out that there is no situation where the force and the magnetic field can be in the same direction due to some direction of the current. Okay, so this one says that this force can't be caused by a magnetic force. Okay, let's move on to the next one. And so this one now is kind of putting together, instead of having a single wire, we have well, we still have a single wire, but this is a wire that's closed on itself in the shape of a square. And so this one says, what is the net magnetic force on the loop of wire shown below? Direction of the current is going to be clockwise. And so think about, for each segment of the wire, what the direction of the force is going to be. Okay. Okay, so let's talk about this one. So here we have this square loop of wire in the presence of a magnetic field that is going to be pointing up. And we're told that the current in this loop of wire is going to flow in the clockwise direction. And so that says that the current is going to go around like this. And we want to find what the net force is acting on this loop of wire. So here's our current. Let's say this is current I. This is magnetic field B. And we want to find what the net force is. And so what that tells us is we need to find what the force is on each individual segment here. So I'm going to label all of these. So we need to find what the force is on 1, 2, 3, and 4. And then we can add all those up to find what the net force is going to be. So let's first start by asking ourselves what the direction of the force is on 1. So in order to find the direction of the force on 1, this is just going to say point our fingers in the direction of the current, curl in the direction of the magnetic field. Force 1, so force 1 is going to be pointing out. Okay. Now let's look at force 2. Force 2, we have the current going in the opposite direction as the magnetic field. These two are not perpendicular to each other, they're anti-parallel to each other to be more precise. And so because they're anti-parallel to each other, there can't be any force imparted on this wire due to this magnetic field. So this one has no magnetic force associated with it. So let's look at 3. So for 3, We have our current going to the left, so fingers in the direction of the current. Magnetic field is pointing up, curl in the direction of the magnetic field. This one is going to be pointing in, okay? Now, the next one that we want to do here is going to be the force for 4. And so we see here that the direction of the current and the direction of the magnetic field are the same. And because of that, there's no force for this one. So this one's 0. So we've determined what the direction of the forces are for each of these. Now, we don't explicitly do the calculation here. We aren't told the dimensions of this, but we can reason through how the magnitude of F1 and the magnitude of F3 should be related to each other. And that's to say that these both have the same length of wire, they both have the same current, and they both have the same magnetic field. And so if I look at this equation here, were I to evaluate this, I would see that the magnitude of F1 and F3 are going to be the same, which says then that because they're in opposite directions, the net force on this loop is going to be equal to 0. Okay? Any questions about that? Now, we will see something kind of interesting here, and it doesn't have to do with the net force, but it has to do with the net torque on this. And so if we think about what this force is going to do, or the net force is going to do, if I have some force going this way, and I have some force going this way, this is going to cause this to spin, right? It's not going to translate, right? Because we remember from last semester that the sum of the forces from Newton's second law, sum of forces is equal to mass times acceleration, right? And so this tells me that if I have some net force acting on an object, that'll cause it to accelerate, to translate, to move in one particular direction. And that's not what we have here, because here we have a sum of forces that's 0. So this isn't going to move horizontally like this, but that doesn't mean it won't move at all. And in this case, this actually means that it's going to spin in one place. And so what we want to do is we want to determine an expression for the magnitude of the torque acting on this loop about the horizontal line that I have drawn here, that is midway between the top and the bottom of the loop. Now, the thing that you also want to take into consideration here is that torque is given by a different cross product, but we're only concerned really with the magnitude of this. But torque, you'll remember from last semester, when you took Physics 1, is defined to be R cross F. Okay? So go ahead and use these pieces of information that I've given you to determine what the torque is acting on this loop of wire about this horizontal line that I have drawn here. Okay? All right, so let's see what we have with this one. So on the last problem, we determined what the direction of the individual forces were acting on this loop of wire. And what we said was that the two vertical pieces have no force acting on them because of the direction of the current and the direction of the magnetic field. But the top and the bottom piece have forces acting on them in such a way that these are going to be in opposite directions. And so what we said was that the force on the top loop is going to be pointing out. So this is going to be pointing out. The force on the bottom loop is going to be pointing in. And so this says that the net force is going to be 0, but that doesn't mean that this isn't going to move at all. Because what's going to tend to happen here, if I have some force acting on the top and the bottom in opposite directions, if I treat this little pad here as my loop, if I have some force acting on it this way and some force acting on it this way, it's going to cause it to spin in place. Okay, and that's kind of the motion that we're trying to coax out of this by trying to calculate what the torque is. And so I told you that I wanted to find what the torque is about this point here, and that this has some distance of d, the current of I, and the magnetic field of B. And so in order to find what the torque is, we first need to calculate what the force is from each one of these. Now, the force is going to be relatively straightforward because we know what I and B are. We know what L is in this case. It's just going to be the length of each segment, which is the distance d. And we also know that I and B are perpendicular to each other. So when I evaluate this cross product, so I say F is going to be equal to L, I cross B. In general, this says this is L, mag I, mag B. times the sine of the angle between them times some unit normal vector. Here we're saying that the sine of the angle is going to be 1 because these are perpendicular to each other. So the sine of 90 is going to be 1, right? So we already took care of this direction here when we did this piece right here, and so we said for the top segment this points out, bottom segment points in, and so the magnitude of each of these forces is just going to be equal to I times L times B, okay? Now, in order to find what the torque is, what we want to do is we want to say that this force acts some distance away from the axis of rotation. This is, sorry, this should just be at D, because L is D. Okay, so in order to find the torque, we need to consider the fact that this force acts a distance d over 2 away from the center of rotation here. And so what that says is to find the torque, we take this force and we multiply it by the distance d over 2. And again, these two things are perpendicular to each other. And so the sine of the angle between the force and this r is going to be 90 degrees. Or the sine of the angle between them is going to be 1. And so this says that the individual torques are going to be d over 2 times the force, which is going to be I d times b. So this says that each torque, I can call this torque 1, and there's a torque 2, is going to be equal to I d squared b divided by 2. But when we want to find what the total torque is, we have two of these. We have one from the top, and we have one from the bottom. And so the total torque, I can write tau total, is just going to be this times 2, which is going to be I d squared times b. That's our total torque. Okay? Any questions about this one? So ultimately, the reason why we're interested in these loops of wire in the presence of magnetic fields is every form of electricity that we generate, with the exception of solar power, comes from loops of wire that are rotating in the presence of magnetic fields. This is something we'll explore next week a little bit more. But basically, any form of power that relies on the generation of steam to spin turbines is dependent on principles of magnetism, where changing magnetic fields can induce currents, and we're always interested in how these loops of wire are going to behave in the presence of magnetic fields. So to give you some examples of these, nuclear power, hydroelectric power, oil and gas, coal. So really a coal power plant, and an oil power plant, and a nuclear power plant all work exactly the same way, in the sense that they're using heat to generate steam, and steam is going to turn a turbine. The difference really is how am I generating the heat, right? So yeah.
I think I must have just missed it, but how did you get rid of the 2?
Sure. The way I got rid of the 2 was because I have 2 of these. I have force on the top, force on the bottom. So there's one torque from the top, one torque from the bottom. I add them together, and because each one of these has a factor of 2 in the denominator, that's going to cancel. Yeah. Okay. So we'll talk a little bit more next week on how it is exactly that changing magnetic fields can produce currents. But like I said, as far as applications of the material that we're learning go, that's probably one of the most important ones, is the generation of electricity. Okay. Any questions about that or what we have here? Yeah.
So just in this point, you said it doesn't matter that like one is pointing into the page and one is pointing out. Like you can just, because there's 2 like top of.
Sure. So I swept a little bit of this under the rug when I took some magnitudes here. But the reason why you add these torques and you don't subtract them is because the torques are going to tend to make them rotate in the same direction. So this one has a force that goes this way. This one has a force going this way. But those work together to make it go around like this. As opposed to if I had both of these forces pointing the same way here, that's not going to rotate, right? Because one's going to try to cause it to rotate that way. One's going to try to cause it to rotate this way. And those 2 torques are going to cancel. So that's why I added them. Yeah. Okay. Other questions? Okay. So let's move on to the next one. Okay, so now we're getting into right-hand rule number 2. And so this question says, the figure below shows the magnetic field lines from a current carrying wire that goes into the board. The direction of the magnetic field lines is clockwise, counterclockwise, or the inner ones are clockwise and the outer ones are counterclockwise. So think about how I define right-hand rule number 2, and then we'll try to figure out what the direction of these magnetic field lines are. Okay, so let's talk about this one. So this question is the first of a couple of questions that are going to be related to right-hand rule number 2. So I laid out right-hand rule number 2 at the very beginning of class, but this is the first time that we're going to be using it. So what right-hand rule number 2 says is, if I have some current carrying wire and I want to find what the direction of the magnetic field is in the vicinity of that wire, what I do is I take my thumb and I point it in the direction of the current and I curl my fingers in the direction of the magnetic field. So in this example, what this says is the magnetic field above the wire is going to be pointing out. The magnetic field below the wire is going to be pointing in. And so let's use that knowledge now to find what the direction of the magnetic field is in this case. So here this says that the current is going to be pointing into the page. So we take our right hand, take our thumb and point it in the direction of the current, and then the direction our fingers curl around in is the direction of the magnetic field. So in this case, this says that the magnetic field is going to be pointing in the clockwise direction. All right, so let's look at the next one. Now the next one is going to combine both right-hand rule number 1 and right-hand rule number 2. So previously, I just told you there is some magnetic field that points in some particular direction, and there's some charge that's moving in the presence of that magnetic field. Find what the direction of the force is. Now, I don't tell you what the direction of the magnetic field is. You have to determine what the direction of the magnetic field is by using right-hand rule number 2. And then you can use right-hand rule number 1 in order to determine the direction of the force. Okay? So go ahead and talk about this one. All right, so let's go ahead and talk about this one. So it's not too bad. You just have to be careful with, take your time, and I think it's helpful to make sure that you draw these things. So in order to find what the direction of the force is acting on this negative charge that's moving to the right, the first thing we need to do is determine what the direction of the magnetic field is. And so we're told that we have this current carrying wire where the current is going up. And so what that says is we can find the direction of the magnetic field in the vicinity of this charge if we apply right-hand rule number 2. And so that says thumb goes in the direction of the current, curl in direction of the magnetic field. Magnetic field is going to be pointing out over here. It's going to be pointing in over here. So now we have the direction of our magnetic field. Now this is just kind of the same as the questions we had before, because we don't care what's going on with this wire anymore. We know what the direction of the magnetic field is. So this says fingers in the direction of the velocity, curl in the direction of the magnetic field. That's going to give me a force that points up. But because this is a negative charge, that needs to be flipped. And so this is going to be a force that points down. Okay? So we've got a little bit more practice with these ones where we have to apply right-hand rule number 2. Now, this one is a little bit tricky. So think about this one. It's going to follow fairly similarly to the one that we have here, but there's a little bit of a difference. So go ahead and talk about this one. Okay, so let's go over this one. So this one follows very naturally from the things that we did in the last one, but the exception here is that the velocity is at this angle of 60 degrees, and so that makes it a little bit more complicated, but not that much more complicated. So the first thing that we want to do when we're looking at this is we know that we have this wire that's carrying this current, and we know that we want to find the force acting on this charged particle. So what we're going to need to do is we're going to need to determine what the magnetic field is that's produced by this wire here. And so in order to do that, we can apply the right-hand rule, more specifically right-hand rule number 2. And that's to say that our thumb is pointing in the direction of the current, fingers curl around in the direction of the magnetic field. And so that says on the left side, we have some magnetic field that's going to be pointing out. And if we wanted to be complete here, we could say that the magnetic field is pointing in on the right side. Now we want to find what the direction of the force is acting on this. And so in order to do that, what we do is we do V cross B. So V points this way. I have to turn my hand over to curl my fingers in the direction of the magnetic field. And that says that my force is going to be pointing like this. Now, this eliminates a bunch of the choices, so we know that the vector for the force is going to be north of east, but we're not quite sure if it's going to be 30 or if it's going to be 60. What we can figure out here is what direction this should be, because we know that these two need to be perpendicular to each other. And so because these two need to be perpendicular to each other, what I have is this is 60 degrees, this is 30 degrees, this is 60 degrees, and then this is 30 degrees. Okay, so this should be 30 degrees north of east. Okay, any questions on this one? Okay, so let's move on to the next one. So now we have something a little bit different. Now we're not talking about the force that a wire acts on a charge. We're talking about the force that a wire acts on another wire. But this still follows from the same methodology that we applied on the last one. We need to know what the direction of the magnetic field is that one wire produces in the vicinity of the other wire. So go ahead and talk about this one. Okay, so let's talk about this one. So we want to find the force that wire 1 exerts on wire 2. And so in order to do that, we need to know what the magnetic field that 1 produces near 2. And so in order to do that, we apply our right-hand rule number 2. We have our thumb in the direction of the current 1, curl in the direction of the magnetic field. This says that over here, magnetic field points this way. Over here, magnetic field points that way. Okay? So now we don't care what wire 1's doing anymore. We know what the magnetic field is near wire 2 from wire 1. And so we can find what the force is on wire 2 by pointing our fingers in the direction of the current for wire 1, or sorry, for wire 2, curling in the direction of the magnetic field that's here, and that's going to give us a force that's going to point to the left. Okay? Any questions about this one? Okay, so let's move on to the next one. So this one says two wires carry current as shown. What is the direction of the force that wire 2 acts on wire 1? So now we're kind of reversing this. We also want to know how could we know what this answer is without using these right-hand rules at all? Just referencing the previous question. Okay, so go ahead and talk about this one. Okay, so let's go ahead and talk about this one. So we could follow exactly the same process that we went through for the first one to do this. So if we wanted to find the force that I2 acts on I1, we could find the magnetic field that I2 creates over here, which happens to be pointing out. We can use that to find the force by saying that our fingers go in the direction of the current I1, curl in the direction of the magnetic field, and this goes this way. But there's another way to do this. And something that I was talking to one of the students about is the fact that Newton's third law always comes back, right? Newton's third law, you'll see it again and again in any physics class that you'll take, or if you take any engineering classes, it becomes even more important there. But we know the direction that I1 acts on I2. This is going to be going this way. So the force that I2 acts on I1 needs to be equal and opposite. So Newton's third law, for a reaction there's an equal and opposite reaction. If we have a force that one object acts on another object, the force that the second object acts on the first object is going to be equal and opposite. Okay. So let's look at the next one. All right, so this is a question about dimensional analysis, and so the equation that I provide here is the equation for the magnetic field that's produced by the current carrying wire. So what we've done so far is we've talked about what the direction of the magnetic field is, but this equation tells us actually what the magnetic field is due to these current carrying wires. And so, for instance, if we had just this one wire here, this has the current I. If we wanted to find the magnetic field here, where this is some distance r, we would say that B is going to be equal to mu naught I divided by 2 pi r. That gives us the value of the magnetic field. Now, this question asks us to find what the units are for the permeability of free space, which is this mu naught term. So we want to find what the units of mu naught are in terms of Tesla, amperes, seconds, and meters, if necessary. So do a little bit of dimensional analysis here to find what the units of mu naught are. Okay, so let's go ahead and talk about this one. So I think we're getting pretty good at these kinds of questions, and these questions come up pretty often, to find what the units are of some parameter in a new equation when we're presented with that equation. And so this new equation is the equation for the magnetic field produced by a long current carrying wire, and it says that the magnetic field B is going to be equal to mu naught I divided by 2 pi r. Now, in order to find what the units are of mu naught, we can remember what the units are for the rest of the parameters here. We know that the magnetic field is measured in units of Tesla. The current is measured in units of amperes. And the distance r is measured in units of meters. And so we can see on the left-hand side of the equation, we have units of Tesla. On the right-hand side of the equation, we have some unknown unit times an ampere divided by a meter. And so whatever mu naught needs to be, it needs to cancel with an ampere and a meter in such a way to leave us with a Tesla. And so what that says is that mu naught, the units of mu naught, need to be Tesla meter per ampere, right? Because this would cancel with the meter here, it would cancel with the ampere here, and that would leave me with a magnetic field which has a unit of Tesla. Okay, good. So now we want to use this equation a little bit more. And so what we'd like to do here is calculate what the magnetic field is at these 3 locations that are shown here. One where we're looking at a distance 1 meter away from the wire 1 on the left, directly in between these 2 wires, and then 1 meter to the right of wire 2. So we're going to have to put together what we learned about the direction of magnetic fields using the right-hand rule with this new calculation, or this new equation that we have. Okay, so go ahead and take some time to work on that, and that might be it for today. We'll just kind of have to see. All right, so let's go ahead and talk about this one, and then I'll let you guys get out of here. So what we want to do is we want to find what the magnetic field is at each one of these points. And so in order to do that, what we're going to do is we're going to apply the equation that the magnetic field is going to be equal to mu naught I divided by 2 pi r. And look at 3 points. So we have point 1, point 2, and point 3. Okay, so I don't have the numbers for this. I'm just going to do this algebraically, but you can just plug the numbers in afterwards. And so for point 1, our magnetic field, the total magnetic field, is going to be equal to, let's call this distance here some distance d. Okay, so this is d, this is d, this is d, and then this is d. So for this point here, we have 2 magnetic fields, one from current 1, one from current 2. This is, the one for current 1 is going to be mu naught I1 divided by 2 pi d. And then we can apply our right-hand rule number 2 to determine the direction that this one points. So finger goes this way, this one's going to be pointing out. Okay? Same thing for current 2, but the distance is further here. So this is going to be mu naught I2 divided by 2 pi, and now this distance is going to be 3d. This points out, okay? Now, for section 2, we have our total magnetic field. each one of these is a distance d away, right? Because this is the distance d, this is the distance d. But the direction of these magnetic fields is not going to be exactly the same that we had in portion 1. So this one says this is going to be mu naught I1 divided by 2 pi d. Now this one points in, right? Because thumb in this direction, curl in this direction, the magnetic field that current I1 produces is going to point in. The magnetic field that current 2 produces is going to be pointing out still. D pointing out, okay? Now, the last one that we can do says this is B vector total is going to be equal to mu naught I1 divided by 2 pi. This is going to give me 3D pointing, what did I do here? This one's pointing in. This is pointing in, this is pointing out, and then this is mu naught I2 divided by 2 pi d pointing in. Okay, and these are going to be plus. Okay, so yeah, question? The 3D comes from the fact that this distance here is 3 times d, right? 1, 2, 3. Okay. Same thing for the first one, for when I'm finding how far away I2 is from this point. It's 3D.
Oh, so you're saying the first half is the mag and the second section is I2?
Yeah, so this is I1, 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 I2, I2, I2 for each point that we're finding. Yeah.
2 and 3, they all crossed out.
What do you mean crossed out?
Like a 0 and an X through it.
Oh, these are indicating the direction the magnetic fields point. So it's into the page, out of the page. Yeah, so the circle with an X is in, circle with a point is out. Yeah. Okay, so that's going to be it for us today. If you guys have other questions, you can come and ask me, but we won't have class again until next Tuesday. Okay, so have a good break.